Hello everyone and welcome to the AI Research Roundup. I'm your host, Alex. Today we're diving into this post from Google Research titled Bridging the Gap in Differentially Private Model Training, published November 25, 2024. This article explores a vulnerability in how differential privacy is applied when training neural networks. Specifically, it focuses on DP-SGD, a common training algorithm. The authors identify a gap between the theoretical privacy analysis, which assumes Poisson subsampling of data batches, and the actual implementation, which typically uses shuffled, fixed-size batches. They suggest this discrepancy weakens the privacy protections and propose a scalable solution using MapReduce for true Poisson subsampling. So this figure illustrates the relationship between the privacy parameter epsilon, and the noise scale sigma added during training. The green line represents Poisson sampling, the ideal but less practical approach. The orange line shows the lower bound of privacy achieved with shuffling, meaning the actual privacy loss could be even higher. Notice how, especially at lower noise levels, shuffling results in a significantly larger epsilon, indicating weaker privacy. Okay, so building on the previous figure, this one shows how the noise scale, sigma, changes with the privacy parameter epsilon. Again, we see Poisson sampling in green, shuffled sampling in orange, and, well, this time we have a new blue line representing deterministic batches, no randomization at all. The key takeaway here is that, as epsilon increases, meaning less privacy, the difference in noise levels between Poisson and shuffled sampling decreases. However, for stronger privacy small epsilon, shuffling requires significantly more noise than Poisson sampling, reinforcing the privacy gap. So this figure explores how the noise scale, sigma, varies with batch size. Again, we have deterministic, Poisson, and shuffled sampling represented by the blue, green, and orange lines, respectively. Interestingly, the noise required for deterministic batches remains constant regardless of batch size. However, for both Poisson and shuffled sampling, the noise scale increases with batch size, with shuffling consistently requiring more noise than Poisson, further highlighting the privacy implications of the shuffling approach. Finally, this figure demonstrates how model performance, measured by AUC, changes with batch size. Deterministic, Poisson, and shuffled batching are shown. All methods improve with larger batch sizes, but importantly, Poisson sampling consistently outperforms shuffled sampling, aligning with the previous findings on noise scales and reinforcing the advantage of Poisson sampling for privacy and performance. Finally, this graph shows how model performance, again using AUC, changes with the privacy parameter epsilon. As epsilon increases, meaning less privacy, all methods generally improve. However, Poisson sampling consistently outperforms shuffled sampling, especially at lower epsilon values, where privacy is a stronger concern. This reinforces the overall message. Poisson sampling offers a better balance of privacy and performance. So to wrap up this fascinating look at differential privacy in machine learning, this post from Google Research really highlighted the discrepancy between the theoretical privacy guarantees of DP-SGD and its practical implementation using shuffled batches. The key takeaway is that Poisson sampling, while less common, offers a more robust and potentially more performant approach to differentially private training. Well, that's all for this week's AI Research Roundup. Thanks for listening.